Hi! In this video, I want to show you a way to intuitively understand chain rule in calculus. What is it saying and why is it true? Particularly in this video, we are going to investigate the following transformation. When replacing the x as a function g of x, we created a compound function. But what exactly happens through this process in terms of rate of change, aka derivatives? Alright, let's start our investigation. Imagine if you don't yet know about chain rule, and you want to figure out the relationship of a compound function's derivative with its components. What would you do? Well, one way to start off is by examining the easiest combinations, where f and g are all linear functions. Let's say fx is 2x and gx is 3x. To find f of g, we replace the x in f by 3x. 2 times 3x is 6x. Their derivatives are 2, 3, and 6, respectively, where 6 is 2 times 3. This is not a coincidence, and we can prove that for any linear function f and g, the derivative of their compound is always the product of each's derivative. And it seems like the values of the two y-intercepts doesn't matter here. This insignificant conclusion might hint us about possible arrangement when we want to extend our pattern to any two arbitrary f and g. Taking a look at our previous derivatives rules, you can see that most fundamental cases contain some hints to what the general form should look like. An explanation to account for this similarity is that tangent lines are really just linear approximation of each point on a nonlinear function. Every point can be seen as equivalent to a linear function mx plus b, with m the slope of the tangent line describing the relationship of that point with its neighbors, and a constant b to adjust the y position. Going back to chain rule, it really makes sense if our final formula is the product of f prime of something and g prime of something, right? Well, you can choose to be skeptical about that assertion. Honestly, when I first heard of this explanation, I was inspired but not convinced. The combination of two linear functions was simply too specific for us to illustrate a general picture. In order to convince ourselves that this pattern works, and to see what story does this formula tell, we need to take a look at some more arbitrary choices. Part 2. Let fx be x squared, gx stays linear, and their compound, f of g of x, be denoted by h. Since f and g are all simple graphs, given the graph of them, how do we construct the graph of h? In other words, what stories does f of g of x tell us? Let's break it down. For us to get the value of h of x, of an input x, we need to first map x to g of x, that is, to find the corresponding y value on the graph g of a given input x. The next step is to map that y value of g to f of y. And how do we do that? Well, a trick to visualize that process is to project the point onto the line y equals to x, and then treat the x value of that point as an input to find the y value on the f graph. Now, this y value we obtained is the result of mapping x to h of x. Ignoring that process though, in short, this is often known as function transformation, which you might have learned in a normal algebra class. In terms of function transformation, f and g are all the same type of functions, while the latter one was just horizontally stretched by a factor of 2. And our question is, how does that horizontal stretch affect the rate of change? Let's have 4 points. I'll put our x back to 2, and use our construction tool. We pick f1 to be 1, f1, and h1 to be 2h2. I picked these 2 points together because we constructed h1 from f1. They share the same y value and have the same relative position on the function trace. We do the same thing again for, let's say, x equals to 4 to obtain another pair of points. And what is the relationship of the pair of secant lines? Our intuition from function transformation tells us that the secant line should be also horizontally stretched by a factor of 2, just like the function itself. And that instinct is absolutely correct. Since those with the same subscript have the same y value, f and h have the same dotted y. However, on the other hand, because the function is horizontally stretched by a factor of 2, it will double the distance for x to travel to reach the same changing y. Therefore, the slope of a secant line of h is always a half times the slope of its corresponding secant line of f. This conclusion is always true for every pair of a corresponding secant line. And hey, if such conclusion is true for all secant lines, then it must be true for tangent lines too, since tangent lines are just a special case of secant line, where the changing x is very small. So, if I want to find the derivative of h at x, it is really equivalent with finding the derivative of its corresponding point on f, which is f prime of g of x, and then finally multiply it by a factor of 1 over 2, and that's it. You can also think of the role of inner functions f as how input values goes into the outer function f. Imagine if that f and h are in the same trace, and function f means particles in that trace move 1 unit horizontally at a time, while for function h, particles moves only a half unit at a time. Therefore, the time will double for particle h to reach the same horizontal displacement. Okay, I think now it is a good time to go to the final part, to explain why chain rule is true for any two nonlinear function f and g. This is a graphical illustration. Let's now use the natural log of x as linear. Well, yeah, you can still surely view it in the sense of function transformation, that the function was still horizontally stretched, though by a different factor at each point. But that's not going to be straightforward enough to explain why the product of their derivatives still gives the right answer. But remember that I spent a lot of time introducing that construction tool in part 2. Maybe that could be useful here too. Let's try to pick some pairs of points and see if there's a relationship between the slope of the tangent lines. The first thing we should notice is that f and h have the same dotted y, for the reason discussed in the previous part. Next, we can also see that dotted y of g is equal to dotted x of f, due to the symmetry of the line x equal to y. Finally, we can see that dotted x of g and h are equal. They are driven by the same change of dx. The only difference is the dotted x of function f, which it was not driven by the same dx. It was driven, in fact, by the dotted y of g. With everything mentioned above, you can easily deduce the equation on the top. And when the chosen dotted x is very small, these three equations means the same thing. Why? I guess I will leave that final thinking to you. I hope this video could be inspiring, and thank you for watching.